Yeah, so hello, both of you. Yeah, so today we're going to do the correction of the midterm. I'm going to release problem set 5 this weekend, so then that'll be for next week. So this first question in the midterm was a multiple choice question. Hopefully you remember that in the tutorial I said it was multiple possible answers could be correct. So hopefully you consider that when you were looking at the questions. So in this first one, we can describe the entire class of context-free languages with, well, we know that we have, by definition, context-free grammars. So the set of languages that can be generated by context-free grammars is, by definition, the context-free languages. And also, we saw when I gave the guest lecture about the conversion algorithm from sort of NPDAs to CFGs and sort of vice versa. NPDAs are sort of equivalent in CFGs because there's a conversion algorithm, right? So these two things are true. You cannot describe, you cannot describe context-free languages with DPDAs because, for instance, WWR, you sort of need to sort of guess at some point that you're past the middle, so you can't really do that with a deterministic PDA. There's no guessing allowed in DPDAs. And then epsilon NFAs, well, those just describe the set of regular languages, right? So, and those are a strict subset, a proper subset of context-free language. So it was only the first one and the third one. The second question was, you have L, which is a context-free language that does not contain the empty word. For every context-free grammar that generates hello, generates L, there exists an equivalent context-free grammar such that so let's see. You can definitely convert any context-free grammar that generates L without the empty word to Chomsky normal form. That's why there's a conversion algorithm. So this is definitely true. And part of the conversion algorithm is the simplification, where in the simplification we remove all epsilon production rules. So this is also definitely true. Unambiguous, this is not true. You cannot always disambiguate a context-free language. So there's such a thing as inherently ambiguous languages. Okay, so this was not true. And then LL1 grammar, to be honest, I actually had to look this up in the slides to know what this was because I had forgotten. LL1 grammars are sort of subsets of unambiguous sort of context-free languages. And so we just said that, L could be inherently ambiguous. So this is also not going to be valid, right? Because this is a proper subset or it's a subset of unambiguous languages. Okay, cool. For C, you have a context-free language and you have a context-free grammar, a string of length n. Then if you use the CYKS algorithm, you can check the membership of CYK in, to create the table, you get n squared, and then to check every single sort of partition, that's n, so then you get n squared n, so that's n cubed. So that's why the algorithm is cubic in time. D, you have two context-free languages. Which of the following assertions is always true? Well, we know that context-free languages are closed under the union, so this is true. They're also closed under the reversal. This was in problem set 4. And they're closed under the star. So that means that these two are context-free, so then you union them. This is also context-free. We know that they're not closed under the intersection. This is not valid because, for instance, if you take something like AN, BMCM, intersected with AM, BMCN, then, this is AN, BNCN, which is not context-free. But these two are context-free, right? So that's why that can't be true. Then this guy maybe was a bit more tricky. Essentially, if you say, well, suppose L2 is the set that contains the empty string, then what you're really saying is that for any L1 complement is context-free, which would mean that context-free languages are closed under the complement, which is not true. Okay, so this was also false. So there was only 1 and 4 that were correct. Lastly, we want to show that WW is not a context-free language using the pumping lemma. This question was why in one of the tutorial videos there was WWW, right? It was kind of on purpose. And so you'll recall from this video, you can't do something like A 3P. So it's the same idea here. You can't do something like A 2N, right? Same idea. This string isn't even in the language, right? So, because, no matter which way you split it, either here you sort of end, uh, you end with an A, start with an A, you start with a B here, so that's not the same string. So whichever way you cut it, it's not going to be a duplication of W. But these two other strings work because, you have WW, WW in both cases. And if you think about the cases, you can pump up here. You can do the sort of straddling, like you get a mismatch thing here. Well, I guess you would need to intersect it, but whatever. Um, actually, right, it doesn't work. Right, it doesn't work because it's not WW anymore. Okay, that's right. And then if you have the case where, you have part of the string here, you pump up, then you also don't have WW anymore. So that means that these two were good. Okay, cool. All right. So that was for the multiple choice questions. Any questions about?
You need to have partial points for the.
I think he said there's partial marks. Yeah, yeah, yeah. So if you get one of them correct, then you probably don't get all of it. Yeah. But I don't know how much exactly, because I'm not going to be grading. Okay, the next question was about PDAs and non-regularity, right? So remember, this is why in problem set 4, there was a question show that it's, like classify, right? Not regular, context free. So this was kind of the general idea, right? Um, so the first thing we're asked is to draw an N PDA that accepts T. So there are several possible answers to this question. Um, you could do one where you notice that T can be the union of two things. So AI, BJ, where I is greater than J, and AI, BJ, where J is greater than I. And then you make NPDAs for both. So an NPDA for this guy is, you have a surplus of A's at the end. So if you have a stack and your stack pushes X's for A's, then at the end you would want at least one X to transition to an accept state. So, that would look something like, you read an A, you push an X for every one of those. And at some point you're out of A's, so you transition to popping. And then at some point you're out of B's, so then you transition, but only if there's an X at the top. Right, so this is for one part of the union. The other part of the union, essentially what you kind of need is at the very end, if it's you can sort of use this same logic, but at the very end, your stack is empty, but you have an extra B to read, right? So if you're pushing an X for every A, then at some point you run out of A's and you start popping, right? Then at some point, because I have more B's than A's, I'm going to sort of run out of strings of A's to sort of pop for, or X's that correspond to A's to pop for. But that should only happen if I still have some B's to read, right? So if I at least have one B and my stack is empty, then this is good. I can also have extra B's, so I'll put the self loop here. Okay, so then I have two machines for each language, and then I can just connect them with epsilon transitions. Okay, so this is one way, right? There's a few other ways. You could have also, this is one way. Another way was you could use the logic of like the NA minus NB, right? So where you have the stack represents I minus J. And if you have like a surplus of A's, then you have maybe X's. And if you have a surplus of B's, then maybe you have, Y's, right? Then, what does this look like? Kind of the same idea, except that now it's just a bit more compact. So for every A I read, I push. and at some point I'm going to run out. Then here I have to be a bit more careful. If I'm reading a B and there's an X at the top, I pop. If I'm reading a B and I go back to Z naught, then I push Y. And if I'm reading a B and there's already a B, then I push an extra one. Okay. And then the only way that I transition to the accept state is, I'm done, and I either have an extra X, at least one extra X, or at least one extra Y, right? So this was like the more compact way of doing this. There's one other way. I mean, there's maybe another way that you might have thought of, but another way that I was thinking of is you can just design a context-free grammar and convert it to an NPDA like we saw in class. So what's a context-free grammar for AI, BJ, I different from J? Well, in this case, you can sort of use the logic of the union of the languages, and that's also going to help, right? So you can say S gives you S1 or S2. S1 is going to be for I strictly greater than J, and S2 is going to be for J strictly greater than I, right? Then S1, I'm going to generate my A's and B's together. And then at some point, I'm going to have an additional amount of A's here, right? So we already kind of saw a context-free grammar that kind of does this in the tutorial. So I'll do this, and then I'll go to A to generate an extra A. And the base case here has to be I have at least one A, right? So it can't be the empty string. Then for J greater than I, it's kind of the same idea. Except that, I go to B, and then from B, I generate additional B's, and the base case has to be B, right? And then, you can take this grammar and convert it to a PDA. I won't do it in its entirety, but, assuming I do an NPDA that accepts via empty stack, so accepts via empty stack, and assuming Z naught is equal to S, then, I might have stuff like reading the empty string and then S being the top and then replacing that with S1 and so on, maybe one for S1. I'm just not going to list all of them, but this would be the ones for the production rules and then for the terminals. Or like I called them in the lecture, leftmost replacements and leftmost processings. Then for the terminals, it would be, read an A, pop an A, read a B, pop a B. Okay, so this was one other way. I mean, maybe there's other ways. Did anyone think of another way? Cool.
Yeah, I personally think draw a PDA as simple as possible.
Yeah, this is fine. These are all simple. Yeah. It was mostly just so that it wouldn't be like overly complicated. But you don't really have to justify that it's simple. Yeah. Other question? Or that was the same question? Same question. Okay, cool. Nice. Was there anything else that I needed to say? Specify how your PDA accepts. Okay, so here it accepts via accept state. Here it accepts via accept state, and the other one accepts via empty step. Cool. All right. Yeah. Yep. Yeah. 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 No, not really. This is good. Yeah. Yeah. I think, yeah. Cool. If it's not good, come talk to me. Okay, cool. Question B, what is the language L of A star B star minus T? So L of A star B star, that's any number of A's and then any number of B's. And then you're taking away all of the strings where the number of A's is different from the number of B's, right? So then the only strings that you're left with are when you have the same number of A's as B's, right? So then the result of this operation is A and Bn, where n is greater or equal to 0. Okay, cool. And then we want to show that T is not regular. Well, suppose it is, using the hint from B. Suppose it is regular. So let's be, suppose T is regular. Then by the closure properties of regular languages, you have one regular language. So why is A star B star regular? Because there's a regular expression that denotes it. So definitely is regular. And T is regular by assumption. And we know that regular languages are closed under the difference. If you didn't remember that, you could have also said that they're closed under the complement and the intersection. That would have also been good. But then that means that in both cases, you would get AN BN for n greater or equal to 0 is regular, which is a contradiction because we've already seen in class that AN BN is not regular. It's the prototypical unregular language. And this was enough. You could have also done the pumping lemma, but to be honest, if a grader sees the pumping lemma, they're just going to ignore it because, yeah, no need to do it. Cool. Any questions about this? No. Cool. All right. The last one was Chomsky normal form and CYKS, right? So maybe unsurprisingly, hopefully I prepared you enough for this. So G is a context-free grammar, and we have these as the production rules in the context-free grammar. And we want to first do simplification and then conversion to CNF and then CYKS, right? So let's do that here. So let me look at the nullable variables. Nullable variables, which variables here are nullable? Well, there's definitely P gives you the empty string. Is there anything else? No, it doesn't look like it. No, it doesn't look like it, right? So, the base case ends, the recursive case ends at the base case. So that's nice. Now we just have to do replacement with um, replacing P with the empty string in any of the production rules that contain it. So, S, I have the original production rules. And then P could have been replaced by the empty string or can be replaced by the empty string. So I also add S. And then P as well, so I get AB. Then for P, I have APB, I have Q, and then I also have AB because P could be replaced by the empty string. Then Q, there's no P there, so I just leave it as is. And then R, same thing. Okay, so then this is the answer for 3AI. Now for 3AII, we want to identify the unit productions. So unit productions. Let's see, what are the unit productions? So I have S gives me S, and P gives me Q, and that's it, right? There's no like additional recursive cases to think of, so that's nice. So unlike you, I'm gonna be a bit lucky and use my iPad, so I can do copy paste. Fortunately, I heard many pages being turned in the exam. We should have maybe thought of that when we were. Anyways, sorry about that. So S gives you S, you can remove it and you don't have to add anything. So that's nice. P gives you Q. If you remove Q, let's remove Q, then I just have to add the production rules for Q, right? So that's just AQ. Okay, and that's it. Okay, nice. Now next, let's copy this. And let's eliminate the useless production. So really, this is just a non-generating productions. So if we look again here, what's non-generating? Anything where there isn't sort of a base case of strings of terminals on the right? So here, this is generating. This is also generating. This is a pipe, right? Yes. This is generating, but this is not generating, right? So that means that I delete this guy and any guy that has it. So this guy, and this guy. So then in the end, I get S gives you SP, APB, AB, P gives you APB, AB, and R gives you B. Right? Nice. So now I have this as the grammar. Now I need to find unreachable variables. So let's make the graph. If I have S can, of course, reach itself. It can also reach a P because of this guy, but then R is all alone, right? Because it's never referenced in any of these guys. So that means that R is unreachable, so I can delete it. So that means that I'll just copy these two lines. Okay, so then this is my context-free grammar, right? It's not in Chomsky normal form yet, but it's simplified enough that I can now convert it to Chomsky normal form. So let's do that. Write the grammar under CNF. So this is the grammar. Let's introduce the terminal variables, so TA, A, and TB for B, and then let's replace them. TA, TB, TA, TB. And now we need to introduce intermediate variables, just one, right? One for this, right? So that's what I'm going to do. I'm going to introduce x1, which goes to PTB. So that's going to be x1 here and x1 here, and I'm done, right? This is in CNF. Nice. Cool. So this is in CNF. Now I can do CYK, copy CYK. So like I said, I like to do the table the other way, but in this case it was this way. But hopefully you realize that it's the same exact thing. It's just that, imagine that this was like this, right? And it's like the same process. Yeah. So this is the grammar that I have. Now, the base cases are going to be here, right? And then I'm going to go sort of like this, right? So I'm going to do like this, and then like this, like this, like this, right? Okay. So for the base cases, I only have one uh, um, variable that generates each of the terminals. So I have TA, TB, TA, and TB. Then let's see, do I have TA, TB? I have one here and I have one here. So I'll put S and P. Then do I have TBTA? No. So this is empty. Then TATB, that's the same case, right? So I'll put SP. Nice. Now I do, so I did this, now I did this, now I'm going to do this. So here, do I have TA with empty? Well, I can skip that because, nothing's going to be with empty. Do I have S and P with TA? So do I have S and TA? No. Hello, hello. P and TA? No, I also don't have. So that means that this is going to be empty, right? Okay, cool. We're almost done. So just in time for the end. Um, then what about this guy? So for this guy, I want to check, well, the empty set with this, there's no variable to pair TB with, so I can skip that. So really I need to check TBS and TBP. So TBS, there's no right-hand side that starts with TB. So I can just skip it. So at this point, maybe in the midterm, you start getting nervous because, it was like, oh, everything's empty. That's not good. But no, this was what was supposed to happen. In fact, let me just say what the in fact was. In fact, the string that Jérôme initially wanted you to parse was much longer. I was able to shorten it a little bit. So yeah. Yeah.
I think in the format of the PowerPoint, early slides, like at the bottom.
Yeah, that's also fine. That's also fine. Yeah, there's another way of doing it with the slides where you start here. Yeah, it's all good.
Let's push it, right?
Yes, it's the same. Yes. Yeah.
I think the way is better. It feels like a more.
Yeah, I like this way. Oh, you like Jerome's way?
uh,
Okay. Okay, nice. Great, great. I mean, to be honest, I got it from Jackie, so we have Jackie to thank. Um, I mean, he didn't invent this other way, but he showed it to me, and I was like, oh, that's kind of cool. Okay, cool. So the last case to go is to do is this one. Now, TA with empty set, that's not going to work. And empty set with SP, that's also not going to work. So the only hope is if SP and SP, one of these pairs combine. So do I have SS? No. Do I have PP? No. But I do have S and then P, right? Thankfully, it's here and it's the one for the start variable. So thank goodness. So I have S gives me S and then P, and then PS I don't have, right? So really it's just S and S gives you SP, right? Nice. So now we're here and we're asked, well, what's the parse tree? Well, the nice thing about this method is, if you kept track with the arrows, then you kind of already know what the parse tree is. So, it asks for a justification, but, you can just say, I don't know. What did I say? Keeping pointers to lower levels. Sure. I keep pointers to lower levels in the table to know what production rows to use. Cool. So that would be, okay, so I have S, SP, right? And then this S, right, gives you TA, TB. This one gives you TA, TB. And this P also must give you, yeah, so this P gives you TA, TB. And then TA is A, TB is B, TA is A, TB is B, right? And that's the string that we get, which is great. And, you could also double check it. I have S gives you SP. I have P gives me TATB, so that's valid. And S gives me TATB, so that's great, right? And yeah, that was the midterm. Nice. So we finished it in 30 minutes. Nice.
For the last one, the slide I was showing like a view,
Right.
so they keep like the right, so.
Yeah. Yeah, that's probably awesome. Yeah, that's fine. Yeah. 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 Yes. So I forgot to put the,
I just have a question.
yeah.
When you do the like that, first converting to CFG and then the by empty stack,
Yeah.
always guaranteed to only need one state.
Yeah. 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 Yeah, you can prove it that one state is good. You can also do it, you can convert this to something that uses an accept state, which is also fine. Um,
Just,
yeah, you have to add, well, you have to add, yeah, one that adds like a special, like the other way to do it would be, you take this and then you do something like, um, if Z naught is the bottom of the stack marker, then you replace it with S Z naught. Then the PDA does its computation, which reproduces the leftmost derivation of the CFG. And then when it's done, then what you should see is Z naught, right? Because S should be popped off. So then you have this, and then you can go to the accept state. That's the other way to do it. Yeah. Nice. Any other questions? You seem like you have another question.
no, I'm just trying to see, for example, ABAB or ABAB, so is they are accepted or not?
ABA, no, right? No.
Design as a conference-free ground and convert.
No, it's just dry NPDA. But you could do it many different ways. We saw many different ways. You don't have to do all of them, just one. So, yeah, I mean, to check that ABA doesn't get accepted, you would have to just go through all of the ways that you would try to generate it with the context-free grammar. And that's basically all the ways that your PDA could try. Because there's a mapping like between the derivations and the PDA's computation. Yeah. 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 Last year it was maybe like let me think. It was like 70-30, 70 new stuff, 30 old stuff.
So then it become more.
Yeah. Yeah. Nice. Cool. Any other question?
It's here recording, I don't know what the stuff is.
Oh, yeah, it's recorded. So I mean, but maybe we're good for the midterm solutions. Cool. All right. Great. Well, thanks a lot for joining or watching, and see you next week. So next week, I'm gonna release problem set 5 over the weekend, and we'll start to 6. Yeah.